The history of humanity is narrated through the energy we utilize. Initially, we relied on our muscles, then we learned to control fire. We shaped the world using coal and oil, and entered the atomic age when we mastered nuclear fission. With each step, we increased our energy output to unprecedented levels. Currently, we are gradually transitioning to renewable energy sources, and if we are fortunate, fusion energy might become viable in the future. As humanity progresses further, assuming we don't destroy ourselves or our habitat, we may gain complete control over our planet's resources. At this stage, we will likely begin searching for new places to expand. However, space is challenging and requires serious human commitment within the solar system. Fortunately, we know where to find an abundant source of energy: the sun. The sun, the ultimate source of energy, outshines our most efficient nuclear reactors by 100%. It radiates power equivalent to trillions of nuclear bombs per second. So, how do we harness this energy? Not just some of it, but all of it. To truly gather the maximum amount of energy, we will need to construct the most ambitious structure in the cosmos: a Dyson Sphere. A Dyson Sphere is a colossal structure that encompasses an entire star to capture its energy output for intelligent species. Building a Dyson Sphere is a technological leap on par with the discovery of fire for our ancestors, transitioning us from a planetary species to an interstellar one. It would mark the beginning of an age of exploration and expansion beyond our wildest imaginations. So, what would it look like? The solid shell enclosing the sun might not be the way to go. Such a massive object could be prone to disruptive effects, drifting, and potential direct collisions with the sun. A more efficient design for a Dyson Sphere could involve a cluster of Dyson swarms, an immense collection of orbiting panels that gather and transport solar energy elsewhere, like a harvested field. Constructing such a structure won't be easy. The sun is incredibly massive, so we would need a vast number of satellites. If each satellite has a square kilometer of surface area, we would require around 30 quadrillion of them to encircle the sun. Even if built with the lightest possible materials, we would need approximately 100 quintillion tons of resources. Additionally, we would need energy to assemble the components and deliver them to their locations around the sun. To create a permanent infrastructure in space for initiating construction, let's assume, for the purpose of this video, that our descendants will be interested in it and want to create this gigantic structure. We can categorize the challenges into three main areas: material design, energy acquisition, and the massive quantities of raw materials needed for our Dyson swarm. To acquire the required raw materials, we would need to dismantle an entire planet. Among the available planets, Mercury is the prime candidate. It is the closest to the sun and rich in minerals. Being near the sun also means less gravitational pull, and Mercury lacks an atmosphere, making it relatively easy to launch material into space. After that, we must consider a simplified design for our Dyson swarm. Traditional solar panels are highly complex and have limited range. Our satellites need to operate at a larger scale and be efficient in gathering and transporting energy. Furthermore, the construction of a Dyson swarm would require careful planning and coordination. The satellites within the swarm would need to be positioned strategically around the sun to maximize energy capture. They would also need to maintain stable orbits and be equipped with advanced propulsion systems to adjust their positions as needed. As we embark on this ambitious endeavor, we must also address the challenges of material design. Traditional solar panels may not be suitable for the scale and requirements of the Dyson swarm. We would need to develop new materials that are lightweight, durable, and capable of efficiently converting solar energy into usable power. Advanced nanomaterials and innovative engineering techniques would play a crucial role in achieving this goal. Additionally, the energy acquisition process is a fundamental aspect of constructing a Dyson Sphere. We need to develop advanced energy collection and transmission technologies to efficiently harness the sun's immense power. This could involve utilizing highly efficient photovoltaic systems, advanced energy storage solutions, and wireless energy transfer methods to transmit the captured energy to distant locations within the Dyson swarm. It's important to recognize that building a Dyson Sphere is an unprecedented feat that would require immense resources, technological advancements, and a collective effort spanning generations. The construction process itself would be a monumental undertaking, requiring sophisticated robotics, autonomous systems, and advanced manufacturing techniques capable of operating in the harsh conditions of space. However, the potential benefits of harnessing the sun's energy on such a scale are staggering. A completed Dyson Sphere would provide humanity with virtually unlimited energy, enabling us to meet the ever-growing demands of our civilization and explore new frontiers within our solar system and beyond. In conclusion, the construction of a Dyson Sphere represents the pinnacle of human ingenuity and technological achievement. It signifies our transition from a planetary species to an interstellar civilization capable of harvesting the immense power of our nearest star. While the challenges are formidable, the rewards of unlocking limitless energy and expanding our horizons are truly awe-inspiring.